Welcome to the Ocean's Atmosphere and Climate Unit launch video. My name is Ruben. I'm a 6th grade science teacher in San Francisco, California. The big unit question: what determines the air temperature of a location on Earth? Before we begin, get those usual resources out. The unit overview, unit at a glance, and standards. Read and annotate the science background knowledge, and then print out your unit internalization guide. Pause here if you haven't done so yet. Why does this unit matter? The climate is changing, and this impacts us every day, no matter where you live. There's also an election coming up, and this is going to be a huge topic of discussion among those candidates and the people paying close attention. It'd be awesome if our students were a part of those conversations. Chapter 1 question: what determines the air temperature of Christchurch, New Zealand? Students are playing the role of climatologists. They're investigating El Nino and its effects on Christchurch, New Zealand. They find out early on that Christchurch experiences cooler than normal temperatures during El Nino years, and this is affecting the crops. Students investigate how does air get energy. They're presented 2 claims and they're asked to share their initial ideas on them. Is energy transferred from the sun to the air directly, or is energy transferred from the sun to the surface and then to the air? They then investigate using this setup you see on the right side. This is in lesson 1.3. Students will find that the air above the surface gets much warmer than the air with no surface directly underneath it. The key concept there is energy from the sun is transferred to Earth's surface. Some of that energy is then transferred to the air above the surface. They also learn that the closer a location is to the equator, the more energy it receives from the sun. Therefore, a location's air temperature is affected by its distance from the equator. Here's an assessment example from Progress Build 1. Pause here and take a hack at it. So Harbin has cooler temperatures because less energy is transferred from the sun directly to the surface and then from the surface to the air. That is a direct result of its distance from the equator. So the amount of energy transferred from the sun to the surface of a location depends on the location's latitude. The Chapter 1 focus task. Students are given 2 locations, A and B, one at the equator and one at the South Pole. They're asked to model how the transfer of energy from the sun to the surface and then the air might be different, and to approximate the temperature in those locations. Pause here and give it a try using the directions you see down in the bottom left. Hopefully this is what you got. The key here is that energy from the sun transfers more energy near the equator, and that's represented with thicker arrows. Thicker arrows are going to demonstrate that more energy is being transferred than what we see at the South Pole with skinnier arrows. And then the students can make the connection that this is what leads directly to the lower temperatures they see in this location. Our Chapter 2 question: other than latitude, what else affects the air temperature of Christchurch? Students are introduced to the concept that an effect may have more than one cause. These may be linked into a chain of causes and effects. We know the location's latitude is going to have effect on the air temperature, but what else might there be? Students start by reading the article, The Ocean in Motion. And the contents of that cargo found its way to different locations across the world. They see that currents are what carry those things and move water across the oceans. They also learn that a current that starts at the equator is going to carry with it warmer than expected water, whereas a current that starts near the poles is going to carry with it cooler than expected water. We then ask students to think about how might that water affect the air above it. They do so by running an experiment that tests the temperature of air above a warm cup of water. They think back to what they did in the previous chapter and how this compares. So eventually they learn that when an ocean current comes from the equator, it brings warmer than expected water to the places it passes, and that water is warmer than the nearby air. When an ocean current comes from the pole, the opposite is true. Energy transfers from warmer substances to cooler substances. Warmer currents transfer energy to cooler air, and warmer air transfers energy to cooler currents. This is going to drive us through the rest of this unit. Here's a progress build for Chapter 2. Pause here, give it a shot, and we'll share our answers in a moment. Hopefully you got it. The air at Alisund is warmer than Katirka. At Alisund, energy is transferred from the ocean to the air. At Katirka, energy is transferred from the air to the ocean. That's a direct result of the differences in currents that go by these two locations. Ocean currents can affect the air temperature of a location by affecting the amount of energy in the surface of the location. In the Chapter 2 task, they really look at using data as evidence. They're asked to compare Buenos Aires and Cape Town and look at the two different currents that go by those locations. Now, these two cities are about the same latitude. So what is going to cause them to be different? The currents. Students are here tested to see if they know exactly how those currents might affect the air temperature in those locations, and then asked to explain. Pause here, give it a shot using the prompt you see, and we'll go over the answer on the next slide. So in Buenos Aires, the ocean transfers energy to the air. In Cape Town, the air transfers energy to the ocean. In this written prompt example, I want you to focus here on the evidence, in green down at the bottom. We saw the same transfer of energy happen in the KIPP experiment. They're bringing back their knowledge, or their writing, to the knowledge they gained in a previous experiment. A perfect use of evidence here. Chapter 3 question. What determines how the ocean currents near Christchurch move? They read about the Coriolis effect, the prevailing winds, and then read about a specific current, the Gulf Stream, that passes over the east coast of the United States. In terms of the Coriolis effect, they're not assessed too deeply on this knowledge, so don't stress it too much. The prevailing winds, and this example of the current and how it moves warm water, are going to be really important moving forward. They then participate in this demonstration that shows how prevailing winds can affect and change the direction of current along with continents. Watch here. Students here see how surface winds can move water and how those water is affected by objects that might change its direction. That's the prevailing winds and continents. Our key concepts here. Prevailing winds and the position of continents determine the direction of ocean currents. Changes to prevailing winds affect ocean currents. Changes to ocean currents affect how much energy is brought to or taken away from a location. It's all coming together now. Our Chapter 3 progress builds. We see here the prevailing winds and two locations that are directly from the sim. What determines the air temperature of these locations, and how can we predict how those currents will move? That's what students are asked to do here. Pause here and take a second to try it on your own. You got it. The air at delta is warmer than alpha. The winds push ocean water that turns and follows the coast. Energy is transferred from the ocean to the air at delta, and energy is transferred from the air to the ocean at alpha. The direction of prevailing winds and the position of the continents determine the path of ocean currents. Chapter 3 focus tasks. Students here are given a current, and they're asked to determine and model how will the prevailing winds move based on the way these currents are moving. They're also asked, as previously, to show the transfer of energy in the zoom-in box and share their approximations of the air temperature, land temperature, and ocean current temperature. Here it is. We see that near the equator, the prevailing winds are pushing the current in a certain direction until it hits Australia. Prevailing winds heading the other direction bring the current back, making that C shape we see there. We also see the transfer of energy in the zoom-in box. The key here is, again, with the thickness of the arrows, showing how the energy transfer is different based on the temperature of each location. Chapter 4 question. This is the science seminar. The students apply what they learned to a new question. So in South China, in the late Carboniferous period, Was the air temperature warmer or cooler than in that location today? Students are presented 3 claims and a series of evidence. Claim 1, it was warmer than it is today. Claim 2, it was cooler. And claim 3, there's no difference, it was the same. They see here the differences in where those locations were now and where they were 306 million years ago. At the end, they're asked to make an argument using the evidence they saw. Was it warmer, cooler, or no difference? Pause here. Give it a quick shot using what you know. So the answer could be one of 2 things. It was warmer, and card C would present that evidence South China was closer to the equator than it is today. Or it was cooler. Card A. Strong prevailing winds would have brought cold temperatures from the South Pole past South China. Now, either one could be correct, but I argue here that claim 2, that South China was cooler, is the more likely scenario. However, there's enough evidence to make an argument for either, and that's the beauty of science and argumentation. Below is an example of an exemplar I've made of a student response of someone who supports claim 2. Really look for students' use of evidence in these examples. The end of unit assessment comes next. Students should be all set, ready to go to crush it. Thank you, teachers, for bearing with me and going through this unit. Thanks for taking the time out to be better for your students. If you're a KIPP teacher, follow these final steps. Look forward to seeing those results throughout the year. Thank you.